Welcome to the Explainer. So you're sitting inside on a sweltering summer day, right? The sun is just absolutely baking your house, and you've probably wondered exactly how your home stays so perfectly chilled. Well, today we're unpacking the beautiful engineering blueprint of central air conditioning. We're going to break down the exact mechanics of how a system keeps an entire building cool even when the outdoor temp is, actively working against you. Okay, let's dive into this, because I really want to start by challenging a common, everyday assumption. Does your central AC actually make cold air? I mean, most of us grew up thinking of our air conditioners like, cold air factories, as if they're magically generating freezing air out of absolutely nowhere and just pumping it into our living rooms. But thermodynamics? Yeah, it tells us a very different story. Here's our roadmap for today. We'll start with the myth of cold air, look at the anatomy of your AC, talk about capturing the indoor heat, compressing and releasing that heat, and finally wrap up with the continuous cooling cycle. Section 1. The myth of cold air. This right here is the foundational rule of everything we're looking at today. Your central air system's true function isn't actually creating cold at all. It's simply moving heat from one place to another. It captures unwanted indoor heat and literally exiles it into the outdoor atmosphere. By continuously absorbing heat indoors and rejecting it outdoors, the system maintains that comfortable temperature you want. It's essentially a high-tech heat transportation network. Once you understand that you aren't adding cold, but rather you're subtracting heat, well, the whole engineering marvel makes perfect sense. Section 2. Anatomy of your AC. To see how this heat subtraction actually happens, we need a mental map of the system's mechanical weapons against the summer heat. Picture a high-quality 3D engineering animation of your home's system. It consists of a few absolutely crucial components working in perfect harmony. Inside, you've got the thermostat acting as the brain, the air handler, the evaporator coil, and your supply and return ducts guiding the airflow. Outside are the heavy lifters, the compressor and the condenser coil, complete with its cooling fan. And bridging them together is the expansion valve. This is the physical board where the whole game of heat transfer is played. Now, what's really interesting about this slide is that these physical components would be completely useless without the lifeblood connecting them all, the refrigerant. Think of the refrigerant as the ultimate thermal messenger. It's this crucial substance flowing continuously inside the system, repeatedly changing its physical state, from liquid to gas and back again, specifically to absorb heat from inside your home and release it outside. Let's actually trace its dynamic flow. Section 3. Capturing the indoor heat. The entire cycle kicks off with a simple electrical signal. Say your room temperature has crept up to an uncomfortable 30 degrees Celsius. You walk over to your thermostat and demand a nice, comfortable 24-degree environment. When the thermostat detects that the indoor temp is higher than your desired setting, boom, it fires an electrical signal straight to the AC unit to wake up and start the cooling cycle. So here is the exact indoor sequence. First, a blower fan pulls that 30-degree warm indoor air through the return ducts. Step 2, that air is forced across the indoor evaporator coil. Inside this coil flows our cold blue refrigerant. As the warm air passes over the coil, heat transfers directly from the air into the refrigerant. You can picture this thermal exchange perfectly, almost like heat transfer arrows in our mental animation. The heat is absorbed, turning that cool blue refrigerant into a much warmer state. Finally, step 4, this newly cooled air is pushed back into your rooms through the supply ducts. The air is cool, but the refrigerant inside the pipes has now effectively stolen all that heat. Section 4. Compressing and releasing heat. So what do we do with this heat-soaked refrigerant? Well, after absorbing your indoor heat, the refrigerant leaves the evaporator coil as a low-pressure vapor. It travels outside directly to the compressor. And the compressor does exactly what its name implies. It aggressively squeezes these vapor molecules together. By compressing them, it turns the low-pressure vapor into a high-pressure, high-temperature gas. It is now scorching hot, far hotter than the outdoor summer air. From there, this high-pressure hot gas moves right into the condenser coil. And this brilliantly illustrates the beautiful engineering dichotomy of the system. Just picture the two opposing coils working together. Your evaporator coil is indoors. Its whole job is to absorb heat, starting with that cold blue refrigerant. Conversely, your condenser coil is outdoors. Its job is to reject heat, acting as a radiator filled with extremely hot red refrigerant. Because the compressed refrigerant in the outdoor condenser coil is hotter than the outside air, the condenser fan blows air across these coils and the heat simply transfers out. The heat from inside your building is officially released into the atmosphere. And as it loses this heat, the refrigerant cools and condenses right back into a liquid.
Section 5. The continuous cooling cycle.
But hey, we aren't done yet. To make this an effective long-term solution, this system has to reset. Enter the unsung hero of this entire operation, the expansion valve. Right now, a refrigerant is a high-pressure liquid. But to absorb heat again, it needs to be cold. So the liquid refrigerant passes through this expansion valve, which acts as a strict bottleneck. As it forces its way through, the refrigerant experiences a sudden, dramatic drop in both pressure and temperature. This almost magical physical reaction instantly chills the refrigerant down, getting it completely ready for another round. Let's summarize the final loop of this complete refrigeration cycle. The outdoor air removes heat from the condenser coil. This causes the hot red refrigerant to condense into a liquid. The expansion valve dramatically drops its pressure and temperature, returning it to a cool blue state. And finally, that newly chilled, low-pressure refrigerant flows right back inside to the evaporator coil. The cycle is complete and the system is perfectly primed to grab the next batch of heat from your living room. So, the crucial point is this: central AC equals heat transfer in action. It's just an elegant, continuous loop of capturing thermal energy indoors, mechanically upgrading its pressure so it can be expelled outdoors, and dropping its pressure to repeat the whole process over and over. I want to leave you with this question to ponder. Knowing your AC simply banishes heat rather than creating cold out of thin air, how does this change the way you view that loud humming outdoor unit sitting in your backyard? Next time you hear the compressor kick on during a heat wave, you'll know exactly what's happening. You aren't just hearing a motor. You're listening to the powerful mechanics of thermodynamics continuously at play, actively defending your home's comfort by throwing the heat back outside where it belongs. Keep learning, keep questioning, and I'll catch you in